In this lesson, we will discuss interaction in multiple regression. Sometimes it's not reasonable to assume the effect of a variable is additive in the model. There may be a multiplicative effect of two predictors on a response. Just like an interaction term in ANOVA, we can test for the interaction in regression. Remember our regression of duration on length and inversions for roller coasters? The scatter plot of the two groups of coasters looks like a non-significant interaction because the slopes look roughly similar. Let's check the p-value to confirm this. An interaction term implies a multiplicative effect on the response. So when we fit an interaction term on length and inversions, R is multiplying those two columns. Here is the output of a multiple regression of duration on length and inversion with an interaction term. Notice that we have added an interaction term to the model as length times inversion. We see that the interaction term is not significant, so it is okay to assume the effect of an inversion in the coaster is just additive. We can remove the interaction term and rerun the model with only the length term and the inversion term. As we saw in our last lesson, if the slopes are the same, the indicator variables can account for differences in the intercepts of the lines. What if the slopes are not the same? Let's compare carbohydrates and calories for selected menu items from Burger King restaurants. Notice that when we look at a scatter plot of the fitted lines for the two groups, meat-based dishes and non-meat dishes, the lines are not parallel. In other words, they have different slopes. How does this impact a regression model with an indicator variable for type of dish? Let's start by introducing an indicator variable called meat, where meat equals 1 if the menu item contains meat, and 0 if it does not. Adding this indicator variable can adjust the intercept of the line, but to adjust the slope, we need to add the interaction term carbs times meat. Notice how this works. If the menu item is a meat-based dish, then meat equals 1 and carbs times meat equals carbs times 1, which equals carbs. If the menu item does not contain meat, then meat equals 0 and carbs times meat equals carbs times 0, which equals 0. Because the carbs term is the linear term in the model, the coefficient of the interaction term will be added to the coefficient of the carb term, therefore changing the slope. We will see this in action when we review the regression equation for these data. Here's the output of our regression model of calories on carbs and meat, along with an interaction term of carbs times meat. Note that the predictor meat is not significant, but the interaction term carbs times meat is significant. Because the interaction term of carbs times meat is significant, we cannot remove the meat term even though it is not significant on its own, because it is part of the interaction term. Thus, we will keep all three terms in our model. Using the coefficients, we see that the intercept of our model is 137.395. The coefficient of the carbs term is 3.93. The coefficient of the meat term is negative 26.16. And the coefficient of the interaction term is 7.88. So the regression equation for this model is calories equals 137.395 plus 3.93 times carbs minus 26.16 times meat plus 7.88 times the interaction of carbs and meat. Now let's find the slope and intercept for the regressions for meat-based items and non-meat-based items. We will start with menu items that do not contain meat. The value of meat for these menu items is 0, so we simply plug in 0 everywhere we see meat and simplify. Notice that neither the intercept nor the coefficient of the carbs term, which is the slope of this model, changes. Now let's find the slope and intercept for the meat-based menu items by plugging in a 1 and simplifying. Note that both the intercept and the slope of this model change. Introducing an interaction term into our model was able to produce a result consistent with simple regressions of our two groups, which had differing intercepts and slopes. In this lesson, we introduced the notion of an interaction using a model with one quantitative variable and one categorical variable. However, an interaction can occur between two quantitative variables as well. If the interaction term is not significant, remove it and rerun the model without it. If the interaction term is significant, the terms in the interaction must stay in the model, even if their individual p-values are not significant.